don't want to say a research paper because it sounds like some stupid English class I took.
Yeah, a research or design paper. Yeah.
Okay, but that just essentially analyzes something that uses the topics that we've discussed here, correct?
Yeah. So you would be applying the techniques of analysis that we've learned so far to a problem. I mean, honestly, it's probably about the same amount of work for you guys, either way. It's just that you would be doing the work without having the unknown test above your heads. You would have it in front of you, and you would know exactly what is required, and you have a bunch of time to do it, but it'd still be a lot of work. So, I did have a class. You guys. The lore has I think it has an exponential decay on it, because I gave the first take-home midterm that I gave students. They complained about it quite a bit. They thought it was really difficult, but two people got 100% on it. So I don't know. I feel like maybe it wasn't that. It was my mechatronics class 4 years ago.
The pros and cons versus this is. If you prepare a lot, if you're a student who prepares a lot for an exam, comes into the exam and fails, versus a student who prepares none and then comes in and fails still, versus if you had a problem in front of you, you put in a lot of effort and then fail, versus someone who still doesn't put in any effort and fails. The risk and reward there is a little different for the effort level of different people.
Yeah. It is different. I do kind of like giving stuff like that because it gives some people don't do well in exam settings, and so I do kind of like those. But I don't know. I don't have. I'll have to think about it a bit. If I can come up with some good ideas for it, yeah. But keep asking me this week, and we'll see if we can come up with an idea by the end of the week. But let's do a few lectures here. We're getting close to being done. We're going to finish up this week in the system dynamics analysis portion of the course. And then we'll move on to probability and statistics and uncertainty analysis. But we have all of the tools that we need at this point. We're just kind of defining a few things, talking about response characteristics, how we can characterize the system, but we know all of the analytical techniques that we need to analyze 0th, 1st, and 2nd order measurement systems. So that's good. So we define 4 transient response characteristics, all defined in terms of a system's step input response. Okay, so that was one of the 2 forms of input that we considered when we looked at 1st order and 2nd order system responses, right? Step inputs. We also looked at sinusoidal inputs. So step inputs are what happens if your measurand, what you're trying to measure, changes from one value that it's at to another value. The response of your measurement system to that change is what's characterized by the step response. And that's what we're going to talk about in terms of its transient response characteristics. For the following, please refer to this illustration in figure 310, this pretty figure here. So the first quantity we'll define is the rise time. So the rise time is the duration from the time the response reaches 10% to the time it reaches 90% of its final value. So this is where it starts out, and it goes up like this. This is a 2nd order response, but it doesn't have to be. We're not defining it in terms of 2nd order or 1st order responses. We're just defining it in terms of how much time it takes to go from here to the final value. So the rise time is the duration from the time the response reaches 10% to the time it reaches 90% of its final value. So the rise time is the duration from this time to 90%, which is this time. So that's what we see here, this time interval. So that's going to characterize how quickly or slowly a system responds, right, to that initial step input, change in the measuring. The peak time, TP, is the time at which the response reaches its first or maximum peak. So this time, right? So assuming that it has a peak, it might not have a peak. So, but if it does, the peak time is the time at which that occurs. So that's going to be another characteristic of like how quickly it responds, right? Some systems have a rise time and don't have a peak time. Sometimes the rise time is more interesting than the peak time, and vice versa. For instance, a system that was first order would respond like this, right? And so it wouldn't have a peak time associated with it. All right, the percent overshoot expresses the amount the response overshoots its steady state value, expressed as a percentage of the steady state value. So the percent overshoot of this system here is this response here is this value, YP, so the peak value, minus the steady state value, which is the steady state value is the value that it's approaching and oscillating about, like way out there, right? So minus that value, so this distance here, divided by the steady state value. So it's like a sort of like a percent error, but it's overshoot, how much it overshoots the steady state value. And it's always as a percent. People like to refer to it as a percent, so that's why we multiply it by 100, and then we call it a percent error. So that one's also useful. And then finally, the settling time is the time at which the response reaches and thereafter remains within 2% of its steady state value. So I'm going to delete these lines because it's a little hard to see. But this gray band here is plus or minus 2% from the steady state value here. So this thing's got a settling time. See, this is the last time that it goes inside these bounds and doesn't leave it. So it goes inside these bounds several times, but it leaves it again. So leaves it, comes back, and it almost leaves it again. And you can just barely tell that it doesn't leave the bounds there. So this is the time at which it comes within plus or minus 2% and thereafter remains within plus or minus 2%. So that's the settling time. And that's going to sort of characterize how long it takes for that system to stop oscillating, or maybe if it's just a first order response, how long it takes to get to that band where it is plus or minus 2%. So those characterize any system. It doesn't have to be first, second, third. It could be any order system, and we could look at its step response like this, and we could define these terms. We're going to come up with these exact analytic expressions or approximations for first and second order systems because we deal with them so frequently. But we could always go back to these definitions. These are the definitions. The other ones are sort of solutions for specific cases. All right. Does everybody get those?
Yeah.
Yeah. There's not. I mean, they're just definitions, right? I mean, when we have a measurement system, clearly we want its settling time to be short, right? Like if you change the thing you're trying to measure suddenly, like a step input, you don't want the settling time to take a long time. You don't want it to take 5 minutes to come to equilibrium. You want it to be at equilibrium quickly. Um,
And this is for, I mean, this is just for like electrical readouts, correct?
so,
Because some things, like for example, a level, if you
Mhm.
wanted to have a digital readout of a level or the angle reading, sometimes if it's moving, it may not take a while before it finally calms down. Physically, it may not calm down, but we're talking about the electrical system, correct? We're not talking about like, if I was trying to balance this on my finger and had a digital readout explaining what was happening, obviously it's going to take a while before it finally calms down, correct?
so it could be any type of signal, actually. So the output isn't necessarily electronic, but it often is.
Okay.
I would say the vast majority of our measurement systems end up being electronic signals. So yeah, often this is an electronic signal, but it probably is corresponding to a mechanical signal. Like if you have a strain gauge that's measuring the strain or stress in something, and you, like for instance, if it was something that was measuring the strain or stress in a beam, and you loaded the beam suddenly, the beam's going to have some response to it. And the beam might be your measurement device. It might not be. It sort of depends on the setup. But if the measurement system is second order, or higher, it would probably have, or it would possibly have an oscillation like this occurring. The electronic system, usually we have enough control of the electronic system not to add like an oscillation to a system that wouldn't already have one. So on the electronic side, it wouldn't make a ton of sense typically to make like a resonant circuit to measure something that's not going to be oscillating. Occasionally that will happen though. It just depends. So yeah, the measurement readout is often electronic. Sometimes the system order is coming from the electronic side. Sometimes the system order is coming from the physical apparatus, the mechanical side. Yeah, but this is something that you're going to see in a lot of measurement systems, though, is that it has to respond to the change in the environment. If it's a temperature sensor, it's probably not going to oscillate because your thermal systems always decay. They don't oscillate. But if it's a mechanical system, you often have some oscillation in it. So if you have a mechanical detector, like in the MRFM case, the mechanical beam that's the measurement device, the motion of that beam is really, really resonant. It really, really oscillates. So you can't just assume that instantaneously whatever force you apply to that beam corresponds to a specific displacement of that beam. It has a dynamic response, and you have to interpret it properly. So this is sort of generic response, and we can use these definitions don't depend on what type of system you have. This is just going to be some system response. Yeah. Yeah, hysteresis.
How do we filter that?
So hysteresis is something that it depends on if your measurement system has hysteresis, you have to account for that when you interpret the results. When we model the system as linear, like we're doing here, hysteresis is not included in that. So everything that you do in a linear system, if you do the opposite to it, it undoes that, right? So, for instance, if you put if you put an input of 2 units in positive into a system, you put in 2 units negative in the system, it does exactly the opposite thing that it would do in a linear system. If you have a system with hysteresis in it, it isn't necessarily the case. So it's a nonlinearity that comes in. And we can deal with it, but it's really specific case-by-case basis. And usually it's in the interpretation of the result that you have to take it into account. An example of hysteresis is when you have a bearing that, so say you're using a milling machine. Has everybody used a mill? Okay, so if you go forward.
Like a windmill or
Oh no,
what are you talking about?
a mechanical milling machine where you're milling off a part, so that so you have a bit that comes down. It's not a drill bit, but
I know what you're
okay. Gotcha. So the mill is driven by these power screws essentially, and if you go in one direction for a while, you'll have really nice, precise control of the motion in that direction. But if you overshoot a little bit where you want to go, and you try to back it up, there's all of this backlash in it, and so you start to reverse it, and you'll not start moving it. You'll start to reverse the motion without actually causing any output to change. And that's the sort of hysteresis where when you're going forward, every turn meant a certain translation, and then you suddenly want to turn the other way, and it doesn't mean that same reverse translation anymore. So that is difficult to deal with, and it's almost like a case-by-case thing. You have to deal with that. So if you're dealing with like a digital controller for one of those things, you pretty much have to measure. You can't just know, oh, this is like a certain number of threads per inch. Like, that's just not good enough. So, yeah. Okay. Great. So this is transient response characteristics, and these are the interpretations.